Medical Imaging with AI
by Veronica Gordivsky and Anastasia Gordivsky. We are building a convolutional neural network that takes a set of X-ray images as input data and determines whether each image is a normal X-ray image or an X-ray image that has pneumonia.
Our baseline model is a convolutional neural network with 12 epochs, a 0.001 learning rate, with 3 convolutional blocks, with one convolutional block having 16 filters, the other having 32, and the last having 64, and all 3 have a kernel size of size 3. We have 1 dense layer, 64 dense units, and we are not using L2 regularization. For our results for the baseline model, we had a validation accuracy of 95.11% and a test accuracy of 91.78%. For our loss curves graph, both the train and validation loss converged to about 0.1, and for the accuracy curves, both the train and validation accuracy converged to about 0.95. Our confusion matrix was actually quite strong, as we had about 200 images correctly classified as normal and 200 images correctly classified as pneumonia, with 25 incorrectly classified for each type of image. In total, leaving us with 400 correctly classified images and about 50 incorrectly classified images. For our simple misclassified test images, we noticed a pattern where the CNN was associating brighter images with pneumonia, even if they were normal.
In order to try to solve the color problem, we decided to change the kernel size of the filters of the first convolutional block from 3 to 5, because the first convolutional block learns simple features such as color. After we increased the kernel size, we noticed that the train accuracy was starting to get higher than the validation accuracy, which indicates signs of overfitting. In order to address that overfitting, we decided to include L2 regularization since it specifically prevents models from memorizing and reduces overfitting.
Our final custom model showed improvement in several ways. One being test accuracy going from 91.78% to 94.44%, validation accuracy going from 95.11% to 95.56%, and our loss curve graph improved, as both the train and validation loss were consistently at lower values throughout the final loss curves, and also both started at lower values than they did in the initial loss curve graph.
Our final takeaway was that even a few minor changes can make huge improvements in training convolutional neural networks, because our final validation and test accuracies and our loss curves improved even after we only made 2 changes.